Here we go. So as we go through this, you guys try them on your own, then hit pause, check it, see how your work compares, see if you got it right. If you did, you're ready, move on. Okay, this first one, the three different families of functions: linear, quadratic, and exponential. So list as many features as you can that describe these three different families. Linear, the graph is a straight line, has some kind of slope to it. Quadratic, the graph is a parabola, looks like a horseshoe. It's symmetric. At the very middle there's a point called a vertex, and we'll get into this later. So everything is symmetric across that vertex. Okay, exponential. Exponential is something like this. Okay, now the pictures are easy to identify. The patterns: linear changes at a constant rate. That is the big key word, a constant rate. And what that means is it's always over 2, up 1, over 2, up 1. The rise and the run, the slope is pretty predictable. It's easy. Quadratic, it's kind of like exponential, and it changes slow, slow, and then it gets fast. So anything with a curve, your change is not constant. Your change is changing. So changes at a constant rate. The quadratic, the second change is constant. And then the exponential is changing at a everly increasing rate. So the linear changes by addition and subtraction, grows by addition, shrinks by subtraction. And that's kind of the same with quadratic. Grows by addition, shrinks by subtraction. Exponential, it grows by multiplication, and it shrinks by division. So exponential changes the very, very fastest. Okay, now exponential. Let's talk about this. Let's look at just the most basic and simple exponential function. If we have okay, well, I guess the equations linear is like 4 equals 2x. You look at the degree. If the degree is 1, you're in the first dimension. That means it's linear. If we've got 4 equals 2x squared, that is a quadratic equation. It's degree 2, second dimension. Exponential is kind of 4 equals 2 to the x. It's when your variable is the exponent. So those are kind of easy to tell too. The tricky part is this next slide, the tables. You got to be pretty good at the tables. So let's go back to this exponential. Here's what you got to understand. So the most basic, easy exponential function to understand. Let's look at something that doubles every day. So y equals 2 to the x, like our penny problem. Okay, now here's what you got to understand. Here's what you got to realize. If we make kind of a little chart here. Whoops. Okay. So, let's say this doubles every day. So on day one, we're going to have a total of 2 items. On day 2, so we're going to call this day, and we'll say the y is the number of items, whatever you got. Day 2, you're going to have 4. Day 3, you're going to have 8. Day 4, you're going to have 16. So your amount is doubling every day as the day goes by. So on day 1, we've got 2, and on day 2 that's going to double to 4, and on day 3 that's going to double to 8, and on day 4, so it gets tall really quick. But here is the $1,000,000 question. So as we go on to day 5, day 6, day 7, it is going to approach infinity. It's getting taller and taller, and it's never going to end. There's no ceiling to it. It can go all the way up to positive infinity, but there is a floor to it. So if we go backwards on day 0, so go backwards, divide them by 2, cut them in half. 8 cut in half is 4, 4 cut in half is 2, 2 cut in half is 1. So 0, you got to dot at 1. Let's go back day -1, whatever that means. Cut 1 in half, and that is a half. So over here, -1, you got to dot at a half. And this is kind of a cool phenomenon what's happening. -2, you cut that dot in half. Half of a half is a fourth. You cut that dot in half. Half of a fourth is an eighth. Then a 16th. So what happens is you go to the left, as you go backwards, you're cutting these dots in half. But no matter how many times, let's say we're out here at -2,653,412. Let's say we're clear out here on the number line, way out to the left. These dots are still gonna be above 0. As you go to the left, they're getting closer and closer and closer and closer to 0. They will never dip down below here. You're never going to have dots down here, because no matter how many times you cut something in half, you will still have a positive quantity left. You can't cut a cheeseburger in half 1,000,000 times and have a negative amount of cheeseburger. So this idea asymptote is in the XIAXLs, it's that dotted line. You're going to have an asymptote at 0. This graph is going to, as time goes on to the right, it's going to get bigger, bigger, bigger. It's going to approach infinity. As we go to the left, as we go backwards, it's going to approach this asymptote. It's going to approach 0. It's never going to cross 0. It's never going to go below 0. It's never even going to touch 0. But it's just going to get closer and closer to 0. And this asymptote is kind of an idea that this line is getting close to that dotted line, but it's never going to touch it. So if we skip and look at a picture, okay, these guys right here. So these horizontal dotted lines, these are asymptotes. So this first one right here, as the graph goes to the left, it's getting taller, taller, taller. It's going to approach positive infinity. But as we go to the right, we're cutting it in something, in half, in half, in half, in half. And this is going to approach the number 1. It's never going to go below 1. It's never going to touch 1. It's just going to get closer and closer and closer and closer to 1. Okay. Let's look at identifying them from a table. So which families do they belong to? If you can, come up with the function. Except for the quadratic, don't worry about the quadratic. Okay, this first one, so already look, this is a hint. At 8, we're already in the 770s. So this got big really quick. That's a hint that it's going to probably be exponential. This graph only goes down to 28, and this one goes to 5. So let's look at this guy. This guy, that's the first hint. It is probably going to be exponential. If you think it's exponential, it's going to grow by multiplication. This one's growing. Multiplication, I think we've got it. I think it's times by 2. 3 doubled is 6, doubled is 12, doubled is 24, doubled is 48. So if it's exponential, we want it to fit this. Y equals A times b to the x, and what we just found is b. We found the rate of growth, so it's doubling. Okay, a is our y-intercept. A is going to be 3. So we think we got a function. We think the function should fit y equals 3 times 2 to the x. Test it just to be sure. Let's plug in 3. 2 cubed is 8. 8 times 3 is 24. 3 works. If it works with 2 of them, you're in business. Let's try for 2. 2 squared is 4. 4 times 3 is 12. 2 gives us 12. We're good. So that is indeed the function for the first table. The second one, this one's growing by addition. 1 to 7, that's a change of 6. 7 to 13, that's a change of 6. 13 to 19, okay, well, we know this one belongs to the family of linear. But it's a trick question because it's really not changing 6 every time. Do you remember this formula? Y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. That's really the same thing as saying the change in y over the change in x. Or rise over run. These are all the same thing. They are all slope. So our y's are changing up 6. Our x's are changing up 3. So there's my rise and my run. Change in my y, that's 6. Change in my x, that's 3. So the slope happens to be up 6 over 3. Up 6 over 3, your slope is 2. If it's linear, it should follow the form y equals mx plus b. And what you just found is m. And b is the y-intercept. B is going to be 0, whatever the y is when x is 0. And it's not given, so you got to use a little creativity to find it. So we know this so far. We know your slope is 2. So it's y equals 2 times x. You're trying to find b. So this one, look, it's not going to be too bad. If 1 is giving me a 1, I guess I need to go backwards. Here we go. 1 is giving me a 1. 2 should give me, change it twice. 2 should give me a 3. 3 should give me a 5. 4 should give me a 7. And it does. It's just skipping from 1 to 4 and 1 to 7. So let's go backwards. 0, just change it twice. So 1 minus 2 is a negative 1. My b is going to be a negative 1. Y equals 2x minus 1. Okay. Now this last one, you can, if you look hard, you can see the vertex in this right here. And the vertex is going to be right here. Because look at this guy. One below it, one above it, those are the same. 2 below it, 2 above it, those are the same. 7 and 7, 14 and 14, 23 and 23. So it's going to be quadratic, and we don't need to come up with the function, but here's another way to tell if it's quadratic. So 23 to 14, that's changing, what did that change, 9? So it's going down, so negative 9. 14 to 7, that went down 7. 7 to 2, that went down 5. 2 to a negative 1, that went down 3. 1 to a negative 2, went down twice. So it's changing at a changing rate. Negative 2 to negative 1, that went up 1. and then -1 to 2, that went up 3, and then this is going to go up 5, up 7. So if you go the second time around, -9 to -7, that went up twice, -7, -5, up twice, -5, -3, up twice. Now that's constant, up 2, up 2, up 2, up 2, up 2. That's quadratic. And we don't need to come up with a function yet. Alright, got a bunch of functions. Can you determine if they represent growth or decay? Okay, growth. Exponential growth starts off really small, but then it gets big, big, big. As you go to the right on the x-axis, you go up on the y-axis. It's growing. It's got a positive rate of change, positive slope. Decay starts big, but you're taking away. You're cutting in half, 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 pretty much until you just have a microscopic amount left, and you can still cut that in half. A never-ending amount. So, growth and decay. This first one, this is my rate of growth. I am multiplying 3.8 to the x. That's going to be like 3.8 times 3.8 times 3.8. Every time you're tripling it, you're almost quadrupling it, because you're almost timesing it by 4. So this one's going to be growth. And you got to be careful, because this guy out front can change it a little bit. And this kind of street smarts way, if you type this into your calculator, you can type it in your calculator and look, does the picture look like this, or does the picture start big and then get small? So if you want to use your street smarts, that's a very good idea. Okay, this one right here, 0.4 to the x, so you're timesing it by 0.4, timesing it by 0.4. Timesing by decimals, those are tricky. This one is actually decay. This one's shrinking, because timesing by 0.4 is the same as timesing by 4/10 or 2/5. And if you're multiplying by 2/5, that's a form of division. So you're kind of cutting it in by 2/5 every time. Okay, this one right here. It's tripling. Your rate of growth is a 3, so it's 3 times 3 times 3 times 3. But this guy, here's where it gets tricky. So if we do 3 times 3, that gives us 9. And if we do 3 times 3 times 3, the next one, that's 27. But after you triple them, you have to times it by a -2. So if you times this by a -2, that's a -18. If you times this guy by a -2, that's a -54. So timesing by negative is actually turning it around, and this is shrinking. So this one is decay. Okay, the next one is a trick question. You look at that, and you see the fraction, and you want to say fraction is division, so this must be shrinking. But it's not the case, because 4/3 is actually the same thing as 1 1/3, which is somewhere between 1 and 2. So you're timesing it by more than 1. You're timesing it by almost 1.5. So it is growing. This guy right here, 4 to the -x, if your exponent is negative, that's tricky. That indicates division. So 4 to the -x is really the same thing as 1 over 4 to the x, which is the same as 1/4 to the x. Because here's what's happening. You're doing 1 over 4 times 4 times 4 times 4. So you're dividing by 4, you're dividing by 16, you're dividing by 64. This is decay. So here is the trick. Whatever this is, if it is a number between 0 and 1, it's going to shrink, it's decay. If it is anything bigger than 1, like this one was 1 1/3, anything bigger than 1, that's growth. But all of these fractions between 0 and 1, there's millions of them, so you got a half, you got a 16th, you got 2/5, you got 15/16. As long as your numerator is smaller than the denominator, that means it's less than 1. And any of these fractions that are less than 1 are actually taking away, they're dividing, so they're decay. What you got to be careful of, if you give you a fraction, if your numerator is bigger than the denominator, that means it's a number bigger than 1, and as long as you're timesing it by something bigger than 1, it's growing. So play it safe, type them in your calculator, look at the graph, or you can even look at the table, see if your table's shrinking, see if your table's growing, and double check yourself with street smarts. Okay, now we're going to raise it a level. We're going to give you 4 pictures, and you come up with a function for each of these 4 types of graphs. Okay, these first 2, these top 2, they're not bad. This one is decay. So you started big, and then you're getting small, 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 and you're going to approach, it looks like they took it and they moved it up and down. It was kind of a vertical shift. So our model, y equals a times b to the x minus k. Can't remember what we put, it doesn't really matter, but if you add or subtract at the end out here, that's taking this asymptote, whatever you're approaching, and it's moving it up and down. So this first one right here, your model has to be, I mean, there's thousands and there's an infinite number of correct answers. So you have a right answer, your neighbor has a right answer, they're both right. They might be different, that's okay. But the main thing is this, we've got to have in the parentheses as our base, you've got to have a number bigger than, no, this one's decay. So you've got to have a number between 0 and 1. If it is decay, the base has to be something between 0 and 1, not including 0 or 1. So let's do 1/2. The x and this right here has to be plus 1. So to get it right, I'm looking for 2 things. That's got to be plus 1, and this has to be something between 0 and 1. Okay, the next one. As you go to the left, it's getting smaller, smaller, smaller. As you go to the right, it's getting bigger, bigger, bigger. So this one's growth. Now, for it to be growth, your base has to be bigger than 1. So it could be 1.4. It could be anything as long as it's bigger than 1. And this asymptote, they shifted it down. This is approaching a -5. So out here you got a -5. So those 2 are not too bad. These bottom 2, now they start to get a little tricky. Okay, these bottom 2, the asymptote is a -1, so that's going to be probably the easiest. But what they have done is they've reflected it. So it used to be this. If I reflect this over that asymptote, over this x-axis, it used to look something like this, which is decay. So your base has to be between 0 and 1. It's got to be some kind of fraction. And then out in front, you got to have a negative. You can have a -10, you can have a negative, whatever you want, but there has to be a negative because that's what reflects it over the x-axis. So there's 3 things. You got a negative, you got a number between 0 and 1, and this has to be a -1. Okay, this last one. If I reflect it, it's going to look something like this. Okay, my asymptote, it's approaching a -5, so here you got a -5. And we've got y equals, my base has to be bigger than 1. There we go, but it was reflected, so I gotta put a negative something out in front, and that could work. That would work. That would give me a picture similar to this. Doesn't have to be exactly this, just something that could describe the graph. Okay, then we start solving radical equations. So move number 1, undo anything outside of the radical. I gotta ditch the 3, I gotta ditch the 5, I gotta ditch the radical, I gotta ditch this 12. First things first, outside the radical, so ditch this 12. -12 minus 12, and we got radical 5n over 3 equals a -5. Okay, now stop. This is no solution. It's a trick question, because they are asking you to find the positive root, and they're telling you that the positive root of 5n over 3 is equal to a negative, and that's impossible. Positive roots cannot equal negative roots. So trick question. If you ever have it all by itself and then a negative, you gotta stop. Okay, number 2. Undo outside, you got a 6 and you got a -3. The 6 is multiplying, so you undo addition and subtraction first. +3 plus 3. So you got 6 radical 3x over 3 equals 3. Now you got to undo the 6, undo the times. So divide 6, divide 6. So we got radical 3x over 3 equals 1/2. Now you got to lift off the radical. So you got to square this, square this. 1/2 times 1/2 is 1/4. So you got 3x over 3 equals 1/4. Now we gotta undo, well, you're gonna undo both these 3's, but these 3's are really divide by 3 and times by 3. So if I undo divide 3, I'm gonna times both sides by 3. Then if I undo the times 3, I'm going to divide both sides by 3, so that's like doing something and turning around and undoing it. So that's 3 divided by 3 is just 1. So we got x is 1/4. Third one. Okay, the t is what we got to get to, but it's hanging out with a 6 and a 12 and a radical. And on this other side I got an 8 and a radical 6. So let's lift off this radical. Let's square this. And let's square this. So the left, we got 6t plus 12. On the right, 8 radical 6 squared is 8 radical 6 times itself. So when we multiply, the 8's multiply, that's 64. And the 6's multiply, and that's 36. And that's a perfect square. The radical of 36 is, square root of 36 is just 6. So we really got 64 times 6. And what is that? So on the right side we really got 384, and on the left you got 6t plus 12. So let's undo the addition. -12 minus 12, and that's going to be 372. Then undo the times 6, so divide 6, divide 6. 372 divided by 6, we should end up t is going to equal 62. Okay, last one. Undo outside, let's undo this +5. So -5 minus 5. And you got another trick question. 13. So this time they are asking you to find the negative root. And the negative root can never be a positive quantity. Negative root's got to be negative. So trick question, this one is no solution. Then, okay, this is from a long time ago. We did exponential equations. So the trick is we want the bases to be the same. So first of all, I'm going to go 81 to the negative 1. Oh, to the negative 1. And this one I'm going to go 27 to the negative 1. Get rid of the fractions. We'll look at them as kind of whole numbers with negative exponents, which indicate you're dividing. So this is going to be a lot easier. Now 81 and 27, they're two totally different bases. And I cannot multiply 27 by itself to create 81. 27 times 27 is too big. So I got to change 81 and 27. I got to change both those bases. And just hopefully from your experience, you know 27 can be modeled with 3 cubed. But you can't do 3 cubed. You got to do 3 to the negative 3. And then 81 we can do, how many 3's? 3 times 3 times 3 times 3. 4 3's, so 3 to the negative 4. And now what we've got is we've got our bases the same. So you need to take these exponents, this negative 4 and this negative 3, and you need to distribute to both of those, and you should have a negative 16x plus 4 on the left, greater than or equal to, on the right a negative 15x. So if I do plus 15x plus 15x, I've got a negative x plus 4 is greater than or equal to 0, minus 4 minus 4. I've got a negative x is greater than or equal to a negative 4. But I'm going to divide by a negative 1, divide by a negative 1. You're going to have x. You've got to change the direction of the inequality, less than or equal to 4. Anytime you multiply or divide by a negative, don't forget you got to change the direction of the inequality. Alright, free fall. So if we give you a formula, T is time, H is measuring distance in feet. So I think they're just going to give you some values. You got to plug them into the right spot into the formula. So if a skydiver jumps from an airplane, free falls for 10 seconds, 10 seconds, that's the time. Before opening the parachute, how many feet does he fall? So instead of T, I'm going to put 10 equals square root of H over 4. So now we just got to solve for H, how many feet. So undo the divided 4 times 4 times 4. We got 40 equals square root of H. Undo the square root, square it, square it. So you got 40 squared. So 1600, and what was H feet? So 10 seconds, it's going to travel 1600 feet. Okay, I guess we forgot this guy over here. 36 and 216. 36, if I do 36 times 36, that's 1200, almost 1300. So we're going to have to change them both. 36, move number 1, let's go 36 to the negative 1. Okay, and then we're going to swap out 36, I'm pretty sure, for 6 to the negative 2. I'm just going to times that to the n, negative 2n. Now, the question is how many 6's to get to 216. 6 times 6. Let's try 3 of them. It is 3. So here's what you got. You've got 6 cubed is 216, n plus 5. Your 6's, your bases are both 6's, so if your bases are the same, logically your exponents have to be the same. So negative 2n is equal to 3n plus 15. Don't forget to distribute 3 to both of those. And then I'm going to minus 3n, so I got a negative 5n equals 15. Divide by negative 5, divide by negative 5. N has got to be a negative 3. Okay, and then our radicals, simplifying radicals. Move number 1. These on the outside, they can play together. Change 5/15, change that to 1/3. And the insides play together. Change 4/12 to also 1/3. Okay, now your x's. If you got x cubed on top, that's x, x, x. And you got x to the 6th on bottom, that's x. That's 6 of them. 3 of these on top are going to undo 3 of these on the bottom. So here's what we got. Okay, now on top, really you just have 1. On bottom, we've got 3. I've got x cubed, so I'm going to take a pair out, 3x, and on the inside we got 3x. Okay, now it's just unacceptable to have a square root on the bottom, so times the bottom by square root of 3x times the top by square root of 3x. So on top we've got 1 times square root of 3x. On bottom, square root of 3x times square root of 3x is square root of 3x squared, and this square undoes that square root, so on the bottom you just got 3x times this guy times this 3x. So on the bottom we've got 9x squared. On the top we've got square root of 3x. There's a lot of work. Okay, this one, we cannot have radicals on the bottom, but this one's totally different because this one has 2 terms, 2 different quantities. This has just 1 piece. 1 piece is kind of easy. If it's got 2, you need to multiply it by its conjugate. So 2 square root of 5 minus square root of 6 on the top, and you got to times the bottom, both of them, by 2 square root of 5 minus square root of 6, which is really a 1, and you can times anything by 1 and not change its value. So here we go. 2 square root of 5 times 2 square root of 5 is 4 square roots of 25. 2 square roots of 5 times a negative square root of 6 is a negative 2 square roots of 30. Times the 5 and what's underneath times together, what's outside, like this 2 and this 2, they times together. Okay, now times this square root of 6 to the 2 square roots of 5. In front of here is a 1, so 2 times 1 is 2. 6 times 5 is 30. Times the square root of 6 to a negative square root of 6, that's going to be a negative square root of 36. And because you chose the conjugate, this will always happen. Your center terms are opposites. Negative 2 square roots of 30, positive 2 square roots of 30, that's nothing. Square root of 25 is 5. 4 times 5 is 20. Negative square root of 36, that is negative 6. 20 minus 6, on the bottom we've got 14. A nice whole number. Okay, the top. Okay, square root of 8. I'm going to change, might be easier to change that first. Square root of 8, if you break down 8, 8's got a perfect square and it's 4. There we go. Square root of 4 is 2, so we got 2 square roots of 2. So change 8 for 2 square roots of 2. Okay, so 2 square roots of 2 times 2 square roots of 5 is going to be 4 square roots of 10. And then 2 square roots of 2 minus, or times a negative 6 is going to be a negative 2 square roots of 12. And this one's pretty tough because in 12 there is a perfect square. 4 times 3, and the square root of 4 is 2. So our final answer, well, not the final, close though. 4 square roots of 10. I'm going to take the square root of 4, 2, so that's going to be negative 4 square roots of 3 all over 14. But that's not the final answer because you're dividing by 14, and we can actually divide both of those by 14. 4 square roots of 10 divided by 14, and the minus 4 square roots of 3 divided by 14. These play together. 4/14 is the same as 2/7. So 2 square roots of 10 minus 2 square roots of 3 over 7. This is it. That's your final answer. Alright, 27. The square root of 27 is 9. 9 times 3. Square root of 9 is 3. Take that to the outside. There's already a negative 2. You got to times them. So it's going to be negative 6 square roots of 3. 40, the perfect square of 40 is a 4. 4 times 10. Square root of 4 is 2. 2 times 3 is 6. 6 square roots of 10. 108. I'm not even sure what's in 108. So we can just break 108 down. That's 2 times 54. 2 is done. 54 is 9 times 6. There we go. 9 is 3 times 3. Done, done. 6 is 3 times 2. So, in 108, we had a 3 times a 3 times a 3 and a 2 times a 2. So, the square hiding in 108 happens to be 36. So watch this, 108, if you divide that by 108 divided by 36, it's going to be 36 and 3. And there's my square. So you take square root of 36, it's going to be 6 on the outside, but we just went all the way down, so we took a 3 and a 2, times them, that's 6. And what's left is this 3. And then this and this, these are opposites, so they undo themselves, and you're left with 6 square roots of 10. That's an awesome problem. Okay, this one looks mean. So you've got to double distribute. Square root of 11 times square root of 2 is going to be square root of 22. Square root of 11 times square root of 33 is going to be square root of 11 times square, whoops, I don't want to do that. Square root of 11 times 33. In 33 there is an 11. 3 times 11, so here we go. I'm taking this 11 out. So I got square root of 22. Take the 11 out and leave the 3 in. Just going to kind of simplify as I go. Now negative 6 times 2, that's going to create 6 times 2. In 6 is a 2, so I'm going to take this 2 out. So it's going to be negative 2 square roots of 3. And then there's going to be something with 6 and 33 too. 6 and 33. Because in 33 is a 3 and in 6 is a 3. So I'm going to take that 3 out. And inside I'm going to keep the 2 and the 11. So it's going to be 3 square roots of 22. Okay, now these two play together. 11 square roots of 3 take away 2 square roots of 3 is 9 square roots of 3. And 1 square root of 22 plus 3 square roots of 22 is going to be 4 square roots of 22. Okay, we have made it. The last page. And these look nasty. So, here we go. 6,300. Well, first of all, if we divide by 100, 63 and 100. And there is my perfect square. 63, okay, this is actually pretty easy, because 63 is 9 times 7, and that is a perfect square. So, square root of 100 is 10. Take the 10 out with the 4. So we got 4 times 10. Square root of 9 is 3. Take the 9 out with the 4 and the 10. You got to times it all together. So on the outside, you're going to have 4 times 10 times 3. And that's 120. On the inside, leave the 7. Okay, the x's, if we got 27 of them, how many are going to come out? How many pairs? How many squares are there? So if we got 27, we are taking out 13 pairs, because that accounts for 26, and that 27th stays put. If I got 65 Ys, how many pairs? Ys, that's gonna be 32. 32 pairs is 64, and so the 65th stays in there. And then Z's, if I got 6,300, there's a lot of Z's. How many pairs? Just cut it in half. So that's 3,150. And that guy, oh no, they all come out. All of the Z's come out, so no more Z's left in. And that's it. That is your answer. 3x times the square root of 8x cubed squared is 3x times the square root of 8x cubed times its exact self. 3x times the square root of 8x cubed. This times this is 9x squared, and this times this is this. And this times this is this. This is pretty freaking fun. Alright, last one. 5 and 15. Oh, did we do that one already? I think we did do that one. Oh, it showed up right here. So, we will not do it again. Study hard, make good notes, ace this test, and make your mama proud.